This is remote.
Okay.
Remote teaching for processing for Illinois still. I just gave final exam yesterday, actually.
The midterm.
It's 8-week session. So.
Oh, okay.
We have 8 weeks lecture and then followed by eight weeks laboratory. So it is 8 weeks. So I was teaching the first half, and then another professor teaches the laboratory processing laboratory. Yeah.
All right, Uday, if you want to go ahead and get started, I just sent a reminder to everybody.
Okay. So it's my pleasure to have Dr. Feng here today for our seminar. He is Blue Cross Blue Shield and Adult Professor at North Carolina A&T State University, and his research focuses on high-intensity ultrasound and application of the ultrasound in food processing and preservation. I have known Dr. Feng since I started to apply food science during my high school. I heard a lot of story and research from my aunt, but I didn't have a chance to meet him in person. So it's so nice to meet you virtually today, and hopefully I can meet you in person. And I will let you to have presented right now. Thank you.
All right, thank you, Yuda, for the introduction. It's so nice to see my dear colleagues, IIT. I think I recognize some names. It's great to virtually return to Illinois again. I just left Illinois 3 months ago. Now I'm in Greensboro, my office in Greensboro, in the farm, actually in the farm. But anyway, I think I'm the Blue Cross Blue Shield professor, indoor professor here. Is for urban food system, actually urban food system. But still, I'm food and byproduct engineering, some engineering guy. As you can see, the taste of my presentation is very much, you can see the equations, that kind of thing. By the way, I think in this next 15 minutes, I think 50 minutes, I will give you a quick summary of my research in the past 21 years in Illinois, basically. The focus is on ultrasound, high intensity ultrasound or power ultrasound applications. As you can imagine, it's 15 minutes versus 21 years. It's very, I just can give a snapshot of some of the research highlights. So in terms of from processing point of view, we look at all the processing is to transform food. Basically, food is kind of biopolymers into a certain product with the functionality, safety, and quality, right? And then there are so many different energy forms. If you look at processing industry, not only for food. And then big one, of course, is the thermal energy. We can see in the, I want to have my pointer here. Okay.
We're not seeing your screen. Your screen is not your presentation.
You cannot see my screen?
No, it's just your desktop that's showing right now.
Oh, really? Sorry. Okay, let me new sharing. How about now?
Still your desktop.
It just says it started screen sharing, but it doesn't show your screen at all.
Oh, really? Okay.
There you go.
Yes.
All right. Okay, sorry.
Thank you.
Yeah, I think we are here. So thermal energy is big category. There are a whole bunch of unit operations, drying, evaporation, and also thermal processing operation, right? Pasteurization, sterilization, and so on. And of course, mechanical, chemical, and biological energy forms. But in past, I think 20, 30 years, I think non-thermal processing has become popular. And then there are actually different energy form, physical energy forms that is utilized to perform different processing applications. You can see there's a long list: pressure, electromagnetic, UV light, and the acoustic energy. I think is one of the non-thermal energy, so which is the focus of my research and also the topic for today. So basically, non-thermal energy, non-thermal processing is not like there's no heat produced, which is not the case. Basically, the mode of action is non-thermal versus thermal processing. Okay. So, it's frozen. Okay. Yeah, I'm sorry. I think I cannot move my slide.
Cindy, I think you need to give the co-hoster to Dr. Feng.
I don't have access to his presentation.
You can put me as co-host, right?
Well, no, because we did this, we practiced this and it worked fine the other day when we did our dry run.
Yeah, right, yeah.
If you click on your arrow on the,
Yeah, let me share it again. Sorry.
that's okay.
All right. Yeah, sorry for the glitches. All right, now I can move my screen. So in terms of sound waves, acoustics, I think there is a look at the sound spectrums. There are whole kinds of sound waves. But the one we're interested is the one here from 20 kilohertz to up to 10 megahertz, which is the one above the human hearing threshold. And then in this 20 kilohertz to 10 megahertz, we can also partition into two categories. The first one is power ultrasound, which is the focus today. This one have a relatively low frequency, 20 kilohertz to 100 kilohertz. And the other group is the one we call diagnostic ultrasound, high frequency. The difference is actually not only frequency, the most important thing is the energy level. So for power ultrasound, you can see it's 10 to 1,000 watt per square centimeter. This is the power density. But for diagnostic is pretty low, okay? Basically, the second one, high frequency one, is for medical imaging purposes and for non-destructive detection for industry like submarine, boiler, nuclear reactors. They use this ultrasound to detect the cracks in the metal. But today, I think the focus is power ultrasound, which is one to use to perform different food processing and food preservation applications. Basically, we have a much higher energy level. Yeah, if you look at this power ultrasound, okay, 20 to 100 kilohertz. Normally, we have a probe of tank to produce the sound waves, right? And then you have this kind of sound wave, and basically, we pass the sound wave through a liquid, and then it can produce a bunch of micro scale activities we call cavitation. Basically, you can produce tiny bubbles in the liquid, and these liquid bubbles will go through this process, will grow, and then eventually implode. And at the point of implosion, it can produce a whole bunch of micro scale physical and chemical events, which is very important for ultrasound application. So you look at here's the sound wave, and then here's the bubble, and they eventually have implosion. So this implosion will produce different kinds of activities. So there are two types of cavitation bubbles. One is called stable cavitation. Basically, those bubbles are relatively stable. They can stay in the liquid for up to 20, 30, acoustic cycles. And this, it can produce what? Can produce very high shear forces near the surface of particles, E. coli, you can imagine, and also the produced surfaces. So this can be used to do dislodging of particles from surfaces. Okay, it can also produce shear force to damage the cell membranes. So another group is called transient cavitation. Basically, this can only survive for a few acoustic cycles, and then this is the most dynamic part of the cavitation because when this transient cavitation bubbles implode, it can produce mechanical, chemical events like very high temperature and pretty high pressure, in the high heating cooling rates, and also shock waves in the liquid. And chemically, it can produce free radicals, basically. And then at liquid solid interfaces, it can produce this kind of liquid jet. It's like liquid bullets, okay, very high velocity, and just shooting, impinging on the surface. And then this is very powerful. And I'm going to show you some photos. So this can be used to remove pathogen from the surface, and also can even punch a hole on the surface of the membrane, cell membrane. So basically, cavitation is the foundation for all the power ultrasound applications. Yeah, one thing we need to know is that acoustic field is not uniform in any places. So I'll just give you some examples. ABC, this is what? This is the way to produce the sound waves. For A, we have an infinite long surface, vibrating surface to produce sound waves. And B is piston source. You have a probe, ultrasound probe, right? And it can produce this kind of sound waves. And then if you have point source, and then you follow the spherical sound wave equations. If you look at these equations in the space, they are not uniform for all of them, not uniform. So non-uniformity is a big issue for ultrasound applications, and we need to pay close attention to this, especially for food safety applications. You can imagine, because of this, you don't have uniform treatment in the treatment chamber. You need to find a way to overcome the non-uniformity issue, just like microwaves. Okay, microwaves, we have the turntable, right, in domestic microwave ovens. So this is something we need to be aware of. In my lab, we actually performed computer simulations. So here's the simulation for probe system. You see here's probe, and then the sound wave distribution in terms of intensity. This is better, probably one on the right. You can see at the tip of the probe, you have very high intensity, and that's why the tip of the probe can get eroded. You can produce metal powders from the surface of the tip. So this is the one simulation. And here's another one. We look at the inactivation of E. coli K12. The only difference between these two, left and the right, is the location of the probe. Okay, you can see the left-hand side, the probe is very close to the bottom, and the right-hand side, there's a 1 inch gap from the bottom. And here is computer simulation of the sound wave distribution for the probe, A and B location. And then the bottom is the log reduction of E. coli. You can see B is much more effective, right? B, which one is B? B is here on the right, and A is here. There's 1 log difference. 1 log is 90% difference, right? So you can see this uniformity issue is important. Because of that, we have a totally different log reduction for chamber A versus chamber B, right? So this is something we need to be aware of. In terms of application, normally we are trying to use the power density to characterize different ultrasonic applications. There are many, many applications. So for high intensity application, for example, microbial inactivation, enzyme inactivation, we need to have pretty high energy level to destruct, to destroy, to deactivate the bacteria and also the enzymes, drying, emulsification, extraction, and then there's low power level applications, especially in recent years, it's getting popular. It can be below the cavitation threshold. You need a certain energy level, acoustic energy level to trigger the cavitation. And energy level below this, then you don't have cavitation activities, which is what we call stress response-based minimal processing technology. I'm going to give you a few examples today, okay? So this power density is power per liter per, that's the watt per volume, okay? I think this is the incomplete summary of the things done in my lab in Illinois, actually in the past 21 years. We have done many different things using ultrasound microbial inactivation for food safety applications, enzyme activation and inactivation. We can both increase or decrease the activity of enzyme. For example, we can increase the hydrolysis rate of cellulose into glucose for fermentation purpose. In that case, we increase activity, or we can decrease the activity of the enzymes in orange juice, trying to extend the shelf life. Separations, many separation applications. I'll give you one example today, cutting. And decontamination is one of the food safety applications. And then extraction reactions, elicitation is low energy level applications. I'm going to give you two examples today. And heat and mass transfer enhancement. Drawing is an example. So there are many topics. So today I can only pick a few from the list. So coming back to our subject today, so we can utilize ultrasound to do what? We can improve the microbial food safety for liquid foods and for fresh produce and sprouting seeds. And then we can enhance the nutritional value for fresh produce and the germinating seeds, among others. And so we can improve the efficiency of processing using drying as an example. And also we can improve the quality of the dry products. In terms of, we can treat ultrasound, using ultrasound to modify the functional property of proteins. So I'll give you one example today. And then we can deactivate enzymes, also trying to improve the quality and extend the shelf life. So this will be some of the topics covered today, okay? Okay, so this is a summary of what we've done. Basically, we find that to develop a successful ultrasonic process, we need to, number one, increase cavitation activities. So achieve a process similar to high temperature short time treatment, in thermal processing. But what we have here, I call it the high intensity short time treatment. And manual thermosonication is example. And second, we need to improve the uniformity of the acoustic field. For that, we apply the variable frequency technology. Just look at the cavitation activities to see how we can enhance the cavitation activity. Remember, I mentioned this for the transient cavitation. And then to enhance cavitation activities, we can do two things. First, we can increase the number of cavities, increase number of the tiny bubbles in the liquid. Second, we can increase the power of implosion, make the bubbles more powerful. And the first one we can do, we can first lower the cavitation threshold, that we can produce more bubbles, or we can use variable frequency technology, okay? And in terms of make the bubbles more powerful, we can do what? We can apply external pressure in the system. And then we can increase acoustic energy density by using high energy level. I think first example is liquid processing. In liquid processing, we can define three parameters. One is ultrasound sonication, okay? The effect of sonication, I think we discussed already. The second is heat. Basically, the application of heat can increase membrane fluidity and enhance cell disruption. This is for food safety applications, okay, only. And then the external pressure, application of hydrostatic pressure can make the collapse more violent, and we can have a more rapid collapse. If you look at these equations, I don't think we have time to go into the details, but I'll just give you some basic information. So basically, what we can do is that we want to combine ultrasound treatment with the thermal treatment and with pressure. And this pressure is not very high. It's not HPP, okay? It's only 2 to 5 ATM pressure, okay? And this 2 to 5 ATM is the back pressure in the handling system. Fluid system. If you pump, you pump liquid in the system, and then you can produce this kind of pressure, not very high. And for thermal part, there's no need to apply heat because ultrasound will generate the heat. So we have these three components already. If you have a pump and you have a treatment chamber, apply ultrasound, then you have all these three together. But the combination of the three is called manual thermal sonication. This is till now the most powerful ultrasound treatment in liquid system. So here's the system, continuous flow, a benchtop system developed in my lab, Illinois, around 2005. So this one, temperature can be from 50 to 75, and pressure is 100 to 400 kilopascal. So this is a 1 ATM to 4 ATM. Pressure is not very high, right? So with this system, we perform a whole bunch of experiments, different kind of applications. But I can give you one example here. This is for inactivation of a kit, E. coli K12. We have 0157 data as well in apple cider. Okay. So the comparison is between three different treatments. Green one is thermal. Yeah, green one is thermal treatment. And red one is the manual sonication, pressure plus ultrasound, okay? And black one is the manual thermal sonication, 59 degrees C, 400 kilopascal. And what you can see is the time to achieve 5 log reduction, okay? For thermal treatment is around 4 minutes. And then for the red one, which is manual sonication, 2.5. And then for manual thermal sonication is 1.3 or 4, okay? So basically the combination of these three can achieve a synergistic effect. Here is the definition of the synergistic effect. You can see you can achieve 1 + 1 is greater than 1, right? So this is the one example. We have applications for different applications, but here just one example. If you look at E. coli carefully, here's the control, E. coli K12, and then the rest is you can see here's manual sonication, 40 degrees C, which is pretty low temperature, right? 500 kilopascal, you can see the damage here. And here you can see the rupture of the cell, right? Second one. And you can see here, there's a puncture hole here by sonication, by the cavitation. So for this kind of damage, I think we know it is irreversible, right? There's no way the bacteria can survive, right? So this is another advantage of ultrasound treatment. The treatment inactivation is irreversible. So for some other technologies, I think that's not the case. We mentioned variable frequency technology is one to improve the uniformity and to also enhance the cavitation activities. So basically, we're looking at different frequencies. Okay, here's the bottom one. For one frequency, you can see because of the overlapping of the wave, so you can produce a hot spot and cold spot in the system, right? In the liquid sample, And then in terms of cavitation, you have this kind of just one size bubbles, okay? One size bubbles. But for variable frequency technology, we have different frequencies in the system. And then we have bubbles with different sizes. Oh, the bubble size is connected to the frequency of the ultrasound, okay? For high frequency, you have smaller bubbles. For low frequency, you have big bubbles, okay? Because you have this kind of different frequency, then you can produce a whole bunch of bubbles with different sizes. They're all producing cavitation effect. So combine all this together, you can improve the uniformity, and you can increase the cavitation. You have more cavitation activities, right? So that's pretty important information. So what we use is technology called MMM, which is the multi-frequency, multi-mode, and modulated technology. Basically, you can change frequency, you can change the waveform, you can change so many parameters, but this is a very powerful technology and very uniform technology, okay? If you look at bottom here, this is the image of aluminum foil, okay? And then those tiny holes are produced by produced by cavitation. You can see they have pretty uniform cavitation activities and also very strong cavitation activities with this MMM technology. Yeah, here's an example for enzyme inactivation with MMM technology. This is a tomato enzymes, the pectin, methylaterase, PME, and PG are the two most important enzymes. For hot break, tomato product processing, hot break is the one to inactivate enzymes. So we compare our MMM reactor with the traditional prop system. And then the power density is much lower, okay, with MMM system. Is 0.1, and then the prop system is up to 4.7. So energy level is very low. However, the activation rate for PME, which is this enzyme, and PG is much greater, okay? You can see for PME, the MMM reactor, standard reactor, okay, the rate is 0.32. And then for the traditional prop system, prop is very strong. Prop system is 0.11, the highest, right? And for PG, it's the same story. So this MMM technology can achieve a very high processing efficiency for many applications, not just for inactivation of bacteria and also enzymes, for other things as well. Okay, then I want to introduce some examples about microbial food safety enhancement and fresh produce, and also sprouting seeds. Yeah, this is the system developed in my lab, Illinois, still in Illinois now. This is the first ultrasonic, large-scale ultrasonic washer in the world. We have 5 patents around this time. Basically, you have this we call sub-industrial scale. It's a industrial scale in Europe, but in the US, I think it is sub-industrial scale. Basically, we have these ultrasonic panels in different frequencies, 3 frequencies, and then you can produce through this channel to do inactivation of human pathogens. Okay. This one, remember, uniformity is important. So we did a computer simulation, look into the acoustic energy distribution between the 2 ultrasonic panels. Here's the simulation result. You can see they're pretty green, right? Uniform green colors in between the 2 channels. So from simulation, it is pretty uniform. And then we perform a validation experiment using aluminum foil. Okay, this aluminum foil, we place the 2 black boxes, the channel, okay, ultrasonic panel. Then we place the aluminum foil at location 1, 3, 6, different locations in between the 2 transducer boxes, and then look at the pitting pattern on the surface, which is produced by cavitation. So you can see at all 5 locations, we have this very uniform pitting patterns, meaning that we have a pretty uniform distribution of ultrasonic waves. And then for fresh produce sanitation, quality is important. You can apply very high energy level. You can have 5 log, 10 log reduction, no problem. But you also destroy the produce, right? You damage the plant cells. That's why I perform experiment trying to find optimal energy level. So this is spinach. So we treat with 80 watts per liter. We try different energy levels, and this is the best result. So you can see we have and then put in storage for 2 weeks. Okay, after treatment, the 1, 2, 3, 4, 5, 8, 16 minutes too long. Okay, you have some damage already. So this is day 0, and after 2 weeks, you can see 60 minutes not good, 4, 8, some not good. So yeah, basically 1 minute is fine. Okay, so that's why we decide we can use 80 watts per liter. We treat for 1 minute because in industry previous washing is only around 60 seconds. So we use 80 watts per liter, and then we perform experiments with spinach, with inoculation of E. coli. Then to look at the total plate count, yeast mode, and the E. coli 0157. Basically, we can increase the log reduction almost 1 log, okay, from 3 point something to 4 point something for E. coli 0157 H7. But this is only for 1 leaf, single leaf, okay? Single leaf in the channel. Now we have a whole bunch of leaves in the batch leaf in the sample. We perform the same experiment just for 1 minute, 60 seconds, okay? You can see for E. coli 0157, we can have half log reduction increase in the log reduction in comparison to chlorine. Okay, so this is the inoculation for spinach. We have a lettuce and tomatoes, other data as well, of course, other produce. My time. Now here is an example for sprouting seeds for microgreen production. So we treat seeds of different produce types, broccoli, kale, right? So we treat with water, with chlorine, and ultrasound 5 and 10 minutes. Here is the log reduction after sonication treatment. So we can get up to 2.5 log reduction, probably compared to the initial count. Okay, so this is the after treatment. Then we do sprouting, and after sprouting, you can see the grow back, but still we have a significantly lower count compared to the control, compared to even the chlorine wash sample. Okay, and then we harvest the microgreen, put in storage for 1 week. And here is after 1 week storage. You can see the level of E. coli 0157 H7. So this is for broccoli, and the kale is the same story. Okay, you can see after inoculation, can get over 2 log reduction, and chlorine is 1 log something. Okay, chlorine, and then this is sprouts microgreen, and here is the harvest microgreen put in storage for 1 week. So here's the bacteria count. Here's broccoli, the sample broccoli, okay. There are 4 samples. First is control, second is chlorine, third and fourth ultrasound treatment at different treatment times. We also have an example for biofilm. I think I did not get time to show it, but here is one very interesting one, because in California, they use this one to decore the lettuce, remove the core of the lettuce, and then they ship it to processor plant to cut and washing packaging. So if they use this in the field to remove the core of the lettuce. And this one, there's issue traditionally because they have welding joints here. And then we find out the bacteria just attached to this rough welding joint. With very high population. Okay, so number 1, we improve the design. So here's my new design. And the second one, we use ultrasound to treat this, to eliminate the E. coli. Okay, so here's chlorine, and chlorine plus ultrasound. So with even 1 ppm chlorine, with 1 minute, 60-second treatments, we can eliminate all the E. coli 0157 H7 attached to the surface of this chlorine knife. So with this, we can have ultrasonic washing baths in the field And after coring for a certain time, we can do sanitation, and quickly we can eliminate all the human pests attached to the coring knife. So this is the one for previous application. Okay, then in terms of quality improvement, here's one for orange juice treatment. This is a project done with Coca-Cola, actually. They have a citrus research center in Florida, Central Florida. So basically we take their orange juice, they did pasteurization in their pilot plant, and then we take sample back to my lab in Illinois, using our manual sanitation system, treat for only 30 seconds, okay, 30 seconds. Then we deactivate enzymes, PME is important one, right? So after 30 seconds, you can see the PME activity is the blue line. And during storage for 90 days, very stable blue line, okay? If you have PME activity, then the orange juice will separate very quickly, the pulp will separate very quickly, okay? So cloud stability is a very important parameter for orange juice. And then we measure the cloud stability during storage, okay? With that treatment, you can see this one increase very quickly and then become almost transparent. When this one reaches 36% cloud stability, okay, then this orange is gone, orange juice is gone. But after our treatment, manual sanitation and the thermal pasteurization, is very stable cloud stability. So you have cloud orange juice for 90 days. So we can indeed extend the shelf life, okay? For orange juice, I think ascorbic acid is the most important quality parameter. And from USD regulation, you need to have 25 milligrams per 100 ml during storage. If you have something below this, then this orange juice reach the shelf life. So we measured the ascorbic acid of the orange juice treated by commercial pasteurization in Coca-Cola and also by our manual sanitation method. We look at the time to reach 25 milligram and below, okay? For commercial sample, 43 days. For our sample, 63 days, okay? This is one storage test. And now we run another storage test also for same orange juice. And this commercial fan from Coca-Cola, 63 days, and our technology, 81 days. You can see indeed, we can extend the shelf life using both cloud stability and also ascorbic acid concentration as quality benchmark. Okay. A relative new application is the one we call using ultrasound as a abiotic elicitor. Okay, basically we use this as a kind of physical stimulation to treat plants. It can be seedlings, can be whole fresh produce, can be plant cells, even plant seeds. By doing this, we can trigger the defense mechanism of the plant system and then can produce more secondary metabolites. And by doing that, we can increase the nutritional content of the fresh produce. This is one used by the biotechnology industry to produce medical molecules, basically. But we're the first one using this to treat seedlings, fresh produce, and seeds. Basically, by applying ultrasound, and then you can increase the synthesis of secondary metabolites and also the antioxidant enzymes. And this can improve the sensory safety and nutritional quality of the produce, and then can produce more antioxidants, antimicrobials, and also volatiles. Basically, it enhance the health, enhance the quality, and of course, enhance the health. Here's example for, I think it's tomato. Tomato. You can see treatment. Then by doing this, we can increase this critical enzyme called PAL. I think here's bottom PAL. This is an indicator enzyme for the phenolics pathway. Okay, pathway. It is indicator for the stress response of the plants. So by doing ultrasound treatment, for 1, 2, 3, 4, you can see we can increase the activity very much, especially for 3 minutes treatments. And then we can also increase the phenolic, total phenolics and the antioxidant capacity. And the bottom, bottom is hypothetic mechanism chart made. Here's the ultrasonic energy stimulation and receptor, and pass this to the plant system. Basically, you can upregulate the enzymes, which can produce, can trigger the increased production of this enzyme, and then increase the synthesis of phenolic compounds. With this technology, we treat different produces. Here's an example for sprouting wheat. For this one, the target molecule is GABA, which is here gamma aminobutyric acid, which is a bioactive compound with a whole bunch of health benefits. So here's our treatment system, and we treat different things: wheat, oat, rice, and here's just wheat. Okay, you can see for treatment, 5 minutes, 30 minutes, we can increase GABA content from around 15 all the way to around 65. You can increase GABA content a lot in this process. Okay, so other process enhancement. Yeah, basically we use ultrasound to modify the functional property of plant proteins, pea protein, soy protein, hemp protein. This is still for pea and soy protein. The technology we developed, we call pH shifting plus ultrasound. Basically, we adjust the pH of the system so allow protein to unfold. And then we use ultrasound to chop protein into small pieces. And then we change pH back, and then the protein refold. And by doing this, we can reduce the size of protein aggregates to nanometers. And then we use this as a building block to make nano emulsions and different nanosystems for protection of bioactive compounds. Here's the example using salt protein. So basically here is the initial salt protein, then we adjust pH to unfold protein, then we apply ultrasound here, can be magnesium sonication here, then we chop protein into small pieces, and then we adjust pH back to 7 so we can produce small nano-sized protein aggregates. And using these aggregates, we can do complexation to produce micro capsules, and then to do different things. Here is to protect vitamin D. Okay, so I have two complexation and also nano emulsion. And control is one without protection, and then blue one is one with nano emulsion with UV exposure time up to 3 hours. You can see you still have 60% of the vitamin D recovery. This is just one applications. Okay, here's one interesting. We use ultrasonic to cut different products, fresh produce, and this is the cheese. Okay, with ultrasonic cutting, we can produce very shining cheese surfaces. And not only that, we can increase the quality of the cheese during storage. Here is what is the oxidation, right? Peroxide value. We can very much reduce the oxidation of the cheese by having this kind of shining surfaces. So here's the data. Sorry, it's a big data table. So for 3 cheeses, and cut, without cut, and look at the peroxide value after up to 4 weeks. 4 weeks. In recent 5 years, we developed this we call non-thermal ultrasonic drying technology. Basically, we use ultrasound to dry. Can you see the? Yeah, you can see this is kiwi, right? You can see we can produce mist by doing misting, right? You can see mist produced by ultrasonic vibration. And here's a strawberry. You can also produce mist, misting, right? Right. So this is a very nice technology because we can do drying under non-thermal conditions. Here's temperature curve. You can see temperature is below 40 degrees C, right? And here's apple slices dried with this technology. And this is a very effective technology because you can remove water by doing misting. And misting, there's no phase change, right? Remove water in the form of mist droplets. Second, we can utilize what we call sponge effect of the ultrasound to push water molecules out of the food. For that, we developed different technology. This is our second generation MMM ultrasonic drying prototype. This is supported by DOE grant. So this is the MMM vibrating sheet. You can see they're very uniform vibration, and this is one used to perform drying. Okay, so here's our system. This is a computer simulation of the sound distribution, pretty uniform, right? With this system, we perform different experiments. Here's just one example for apple drying, apple slices, okay? Temperature is 40 degrees, 40 degrees non-thermal, right? 50 is also not very high. Interestingly, the lower the temperature, and then the more the efficiency enhancement. For 40 degrees C drying, for example, with ultrasound, without ultrasound, the time reduction is 70%. Can reduce the drying time by 70%. And also this process can save energy by over 30%. So it can reduce the drying time, also reduce the energy consumption. Okay, so coming back, I think we covered the topics, quite a few topics today. We can see by this point with confidence that the ultrasound technology is promising. For what? For improving the safety of different food products, liquid foods, fresh produce, seeds. Is effective in quality enhancement of fresh produce and germinating seeds at a low energy level. And it can improve the processing efficiency using drying as example. I didn't show you quality data. It can improve the quality as well. And it can improve the functional property of plant proteins, and can deactivate enzymes to improve quality and extend the shelf life. For more information, here's the book published. We put together 10 plus years ago, but still pretty useful. Yeah, I want to thank people in my lab in the past 20 years, postdocs and PhD students and master students. And here's the funding agency for my ultrasound research in the past 20 years. With that, I think I want to be happy to take your questions.
Thanks, Dr. Feng. So if in the audience any question, please unmute yourself to ask.
Yeah, no, I have to go pretty fast today. That's good.
Hi, Dr. Feng.
Hi.
Really nice to meet you virtually. A very interesting presentation, and thank you for doing that. I have one question regarding the abiotic elicitors. Does the effect of ultrasound works on the fruit itself or on the seed?
We perform experiments for starting from seeds before germination and during germination at different germination, the germinating time, and also the seedling in hydroponic system during different stage of growth, and also mature produce. In all stage, I think we can increase the increased activity and then can produce more secondary metabolites, then increase the total phenolics and the antioxidant compounds. But it is produce specific. For different produce, the response is different. And also at different growth stage, the response is different. there's no problem to increase production of secondary metabolites. The problem is how to allow the accumulation of those molecules, because those molecules are produced to counter the stress, right? And this process will consume these molecules. So producing the compounds and accumulation is very important. You need to be careful, play with the parameters, trying to accumulate enough molecules to be measurable, right? So that is the tricky part. You need to have pretty good control of the parameters. And also it's produce specific, each produce is different, yeah.
Thank you so much.
Thank you for the question.
I have a little add-on based on that question. So is there any limitation of what kind of produce you can use for increase the nutritional value? Because they probably different in composition and like the shape of the produce. So is there any limitation you saw before?
Yeah, I just mentioned for different produce, the response is different, right? And also the key is to have uniform treatment, because otherwise you cannot measure you need to have a uniform acoustic field. That's why we design special holder to hold produce to make sure the produce can receive uniform treatment on both sides. So uniform treatment is important. And then for produce, there's optimal conditions. You need to find optimal condition for the maximized accumulation of those secondary metabolites. So each produce is different. You need to run experiment to find the optimal conditions so you can maximize the accumulation of those molecules.
Hi, Hao, this is Wei. Dr. Feng is a good friend of mine. We collaborate in multiple research projects in the past, like 10, 15 years. And it's so nice to listen to your seminar. Very interesting applications of ultrasound in all respects. I just have a quick kind of question I would like to hear from you as an expert in ultrasound. As you know, we are doing using ultrasound for bacterial inactivation in produce washing process.
Mm-hmm.
My PhD student just presented as a part of her research to the thesis committee, and there were some questions about using a chlorine plus ultrasound together. So chlorine is a chemical compound that can impose oxidative stress. And that's the main killing mechanism of bacteria. Well, ultrasound, some people think ultrasound is more like a physical thing to shake off the bacteria that may attach on the surface of produce. That's why it can magnify the killing effect when coupled with chlorine or other chemical sanitizers. I'm just wondering, I know ultrasound can also create free radicals, which is highly oxidative to the pathogen, to the cells. I wonder, in your opinion, if you may, what's the percentage of bacterial inactivation between physical effects versus chemical effects?
Yeah, thank you. Yeah, Dr. Zhang, we've been working with Dr. Zhang for many years, different projects. I think that's a good question. It has to do with the energy level of the ultrasound. If you apply high, very strong energy into the system, ultrasound can rupture the cells, basically. It is a physical effect, it can rupture the cells. It can also produce a lot of free radicals at the same time, but the physical effect is dominant in ultrasound treatment. But for fresh produce sanitation, because we don't want to damage the plant cells, right? That's why we use a low energy level. Low energy level is more of a dislodging, remove the particles from surface. So the efficiency is defined by how efficient you can remove the attached bacteria from surface. because if bacteria is removed from surface into liquid solution, and very easy to kill, right? With 1 ppm chlorine, kill a lot of cells very quickly. So for fresh produce applications, I think it is more a physical effect because energy level is very low. The free radical production is very low because energy is pretty low. But for liquid food processing, like orange juice processing, apple cider processing, we need a very high intensity. And in that case, ultrasound can rupture the cells. It is also a physical effect. You can produce free radicals versus the physical effect. I think the effect of free radicals can be ignored. The research 20, 30 years ago, people trying to figure out the free radical and the cavitation physical effect, which one is more important. And then the conclusion was 20 years ago already, free radical, the effect of free radical, contribution of free radical is minimal in ultrasound treatment, even for high intensity treatment. For low intensity treatment, the free radical can be ignored. Yeah.
Okay, thank you. It's very informational.
Yeah, thank you.
Hi, Ho. I have a couple of questions too. One of the lines in your summary slide was about enhancing the plant proteins. Could you elaborate on that part? Yeah,
I think it is a physical modification method. To modify protein, there are many methods: chemical, physical, enzymatic, right? It is a physical modification method, but it is pretty effective compared to other methods. Right now, people use high pressure, UV light, coplasma, using different things to modify. But also, ultrasound is one of the most effective methods because it is physical. You can physically modify the protein structure, secondary structure, even tertiary structure, even secondary structure. Depends on energy level, treatment time. So we have done a whole bunch of experiments looking into the effect of ultrasound on the secondary structure, tertiary structure, and then look at the functionality, hydrophobicity, forming. You can name it, right? A whole bunch of parameters for the functional properties. It is pretty effective, especially the mesosomal sonication method is very effective. In very short time, you can modify the protein. You can produce subunits, reduce the size, produce subunits, and then you enhance the solubility a lot. For hemp protein is very tough, but we can improve solubility of hemp protein by 2 or 3 folds. Yeah, it's very effective.
Very interesting. I was under the impression that any type of, kind of like ultrasound or other physical thing damages the protein and thus, it make the protein less effective. But it was very interesting to hear that you can improve that.
Yeah, they can.
Fantastic. Also, about the instruments that are in the market, especially in the larger scale, when we talk about the industry, which ones are there, and then how they are advancing? Could you talk a little bit about that?
Yeah, you can purchase commercial unit. Commercial units but they are mostly from European companies, and in the US, they produce small benchtop system. One of the large scale production, I think there are few companies in Europe, they can produce that kind of a system. But there are commercial available system they can purchase for liquid processing. You can pump continuous flow. You can pump the slurry into the system. They can do inactivation. You can do protein modification. Yeah, I think that there are commercial units available.
Thank you very much. Excellent presentation.
Hey, Hao, this is TJ Fu.
Hey, hi, TJ.
Hey, nice to see you. I didn't know you actually left Illinois, so I hope you enjoy life in North Carolina. But anyway, I was just curious. I have actually 2 questions. One is simple. So in our typical ultrasound system, we hear this loud voice. People have to use earplug to put ears. For your ultrasound system, is that sound too loud, or that's?
Okay, yeah, this is interesting, right? People say ultrasound, you cannot hear ultrasound. Of course, you cannot hear. So those are the subsonic sounds produced by physical system, is not by the ultrasound, it's produced by physical system. Yes, if you have high energy level, then they have more, the system will vibrate, right? And more noise, but those are not ultrasound. Ultrasound, you cannot hear it.
Okay.
Yeah.
So it's no danger to the human.
No, still need to have some protection, right? No, yeah, still.
So the other is actually, I'm interested in that drying. You use ultrasound to dry. What is the mechanism behind that water being pushed out of the fluid?
Yeah, that's a good question. I think you can see sound wave, right? Sound wave is one direct, you need sound wave, and then they can produce momentum, right, in the liquid momentum, and then those can produce fountain. Basically, if you have an ultrasound, you put water, then you can see that can produce fountain, right, on the surface of water. It is caused by the we call acoustic driven flow in the liquid, and the liquid on the liquid surface can produce fountain, and those fountain can form mist. It is very complicated mathematically, but basically the ultrasound can push liquid out. Yeah.
Right. Is there a saturation point? Like you apply certain force, then water can come out, but then you got too much water in the air, then the ultrasound will no longer work because the saturation. I don't know. I'm just guessing.
No. You need to remove the mist by airflow. You don't.
Okay. Okay. Yeah, it's interesting. So then, so you did indicate the time is shorter than the typical heat treatment. I wonder, it's like overall, can they do like a continuous treatment so that you can actually do a mass production or mass processing in large scale? Yeah,
that's critical. Actually, right now is batch operation because food must be in contact with the ultrasonic vibrating surface. So it is batch of, just like drum drying. Drum drying is contacting, right? So you have a contact food in contact with the vibrating surface. In that case, it must be batch. Currently, unless you use airborne ultrasound, you can have an ultrasound emission into the air and then onto the food surface. That way you can achieve continuous operation. But for airborne ultrasound, you have a impedance mismatching issue, so it's not very efficient. The quick answer is no right now. Currently, it's a batch operation.
Okay, well, thanks. Well, nice to see you.
Yeah, thank you.
Okay.
Any other questions? Okay, well, I'd like to thank you again for joining us. Special thanks to Dr. Feng for his presentation this afternoon, and wishing everybody the great rest of your day.
Thank you, Cindy.
Thank
Thank
you.
you so much.
Thank you all for listening. Yeah, good to see you guys.
Yes, thank you.
Thank you. Take care.